Okay, Chem 7 people, here is Chapter 8, Saturated Hydrocarbons, PowerPoint. So you know that organic chemistry is when you have chemicals that have a carbon in them. So generally they have a carbon and a hydrogen, and then sometimes they'll have oxygen, sulfur, nitrogen as well. We're going to study organic chemistry because we need to do that before we do biochem, which will be the last unit that we have. And this lecture is all about saturated hydrocarbons, which are called alkanes, and they just have all single bonds in them. So here's the differences between organic and inorganic compounds. And organic has the carbon, and inorganic generally doesn't have them. They have very different physical properties, their melting points and their boiling points, and their chemical reactivity, their combustibility. So look at these properties and just take a look at them and know them, especially the physical properties and the chemical properties. So we did those structures before, and you know that carbon's in group 4, so it has 4 electrons, and so it has 4 places that it can bond. So it has 4 hookups. So that's why carbon can make really long, complicated molecules, because it can bond with 4 other things. And when we're doing alkanes, we're just talking about carbons and hydrogens. And these bonds for alkanes are all single bonds. When we go to alkenes and alkynes, we have double and triple bonds, but this chapter is all about single bonds. So those are all covalent bonds, and we draw them like this. Instead of having the dots, we draw lines because it makes it easier to draw them. And we have to start knowing the prefixes, what they mean. Meth is 1 carbon, eth means 2, and prop means 3. And as you see on these, there's all single lines for the alkanes, and carbon has 4 bonds hooked to it, and hydrogen can only have 1 line hooked to it. So carbon's always going to have 4 lines somewhere, and hydrogen's going to have 1 line. So you have to remember that when you draw. So here's all the prefix names for alkanes. So know 1 through 10, methane all the way to decane, and we're going to generally draw them out in long structures like you saw on the previous slide. And sometimes you'll see them in molecular formulas. So all these carbons are bonding in a tetrahedral way. There's 4 hookups, and they're all spread apart as far as they can in 3 dimensions. And when they do that, they make a degree measure of 109 degrees between the 2 hydrogens. So those hydrogens are trying to stay as far apart as possible from each other. You made these in a lab. When we make molecular models, we put bonds as little sticks, and each atom is a ball that we put on the sticks. So those lines are the bonds, and the little round balls are the different atoms. So here's ways of drawing, or making, models of methane and propane. And the bottom is called space-filling models. When you have, this is the way they really look. They look more like the space-filling models than the ball and stick models in real life. So alkanes can be straight chains, long chains of carbons, or they can be branched. So straight chains are kind of like one trunk of a tree, and branched are like the trunk and a branch coming off of it. So straight chains have one straight line of carbons, but a branched one has the trunk and then a branch coming off of it. So I kind of think of them as a necklace. You have the chain of your necklace, and then maybe you have some beads hanging off of that necklace. So when we have those little branches, we will have little chains of carbons, and when we have those little beads that hang off, we call them YLs. So methyl, when we take off that H and we put it onto the branch chain, it's called methyl instead of methane. So methane by itself looks like this, but if we take one of the H's off and we use this as a bead, we call it a methyl. Ethane has 2 carbons, but if I take one of the hydrogens off, it's called an ethyl bead that goes on that long chain. So propane goes to propyl. And so those are things we add to a carbon chain, and we make it branched using those. So for example, how to name things, we figure out the longest chain first. So for example, this is 7 carbons long, so I'm going to call it a heptane. The longest chain I have of carbons is 7. We also have things hanging off the chain. We have 1 bead here, and we have 1 bead here. And we number the chain in the smallest number possible for these locations. So I have 1 methyl bead on carbon 2, and I have 1 methyl bead on carbon number 4. So there's my bead on carbon 4, there's my bead on carbon number 2. So we name the long chain first. We said it was heptane, and then we said we had beads on there. We have this bead here, this bead there. So we're going to say I have a methyl on 2 and a methyl on 4, so that means I have 2 methyls, so that's called a dimethyl. So the name for the whole thing is 2,4-dimethylheptane. When we make these hydrocarbons in rings, then we call them cyclos. So we name the longest chain first, and we say that we're putting it together in a circle, so we call it cyclopropane. So here's a practice problem. We'll do those in class. Then we have things called geometric isomers that in 3 dimensions they look different from each other. So this is supposed to show a circle of 4 carbons. So think of that like as your hand sitting out in space, and on top of your hand you have 2 H's, and the bottom of your hand you have 2 methyl groups. So this would be called cis because these 2 methyl groups are on the same side. If you had this cycle as being flat on your palm of your hand, and then on top you had a CH3 and an H, but on the bottom you had a CH3 and an H, that would be called trans because the CH3 is across this line of the palm of your hand. We're also going to learn about chirality, which means that molecules can have the same exact formula but be put together in 2 different ways. So that's called chirality, or being a chiral object. So if you look at these 2 things, they have the same formula, they have the same things hooked to the carbon in the middle, but they're put together differently. So they are isomers of each other. So we have to be able to find these chiral centers. This carbon right here is chiral because it has 4 different things hooked to it, and that means you can put it together in different ways. And for example, these 2 different oils. You've had tasted spearmint gum, you know that flavor and smell, and you might have had rye bread. That's the caraway seeds in rye bread. This is caraway oil. They look exactly the same except for this little part right here. Caraway is downwards, and spearmint oil is up top, and it makes these 2 things smell and taste differently. So this carbon that I've highlighted right there are called chiral centers. They are put together differently. The things that are attached to those carbons are in a different order. So it's important for your body because if the attachments to the carbon aren't the same, it may not be able to fit into the receptor molecule in your nose or in other parts of your body that receives the chemical and makes the reaction happen in your body. So we need to have molecules that are set up correctly so they'll fit into the body parts correctly. We talked about this when we did the lab, when we took the carbons and hydrogens and put them together, and then we spun them around the center. We moved this, we moved the bond around and we swung it around. And so that's called rotation. The most stable for this molecule to be in is for all the atoms to be as far apart from each other as possible, as you see up here. But if they're like this, they're kind of close together, and so this takes more energy for them to do this. So this is not as stable as this stable one over here, where everything's always in molecules, the atoms and electrons want to be as far apart from each other as possible. So if you have cyclohexane, you know cyclo means circle and hexane means 6 carbons. That's what this is showing here. In reality, the molecule would prefer to be in this shape here. It's called a chair. It's kind of like a lounge chair in your backyard. You have the head, your head up here, your body's here, and then your legs are hanging down there on the bottom of the chair. This is more stable than the boat way, where the head and the feet are up in the air. So it prefers to be in this formation in 3 dimensions in real life. So every time we talk about different hydrocarbons, we're going to talk about their physical and chemical properties. So physical properties are that these guys, the larger the molecule, the more they like to stay together by something called London forces. And London forces are important, so I need you guys to make sure you understand what London forces are all about. So please study that in the book or online. So when molecules are bigger and bigger, it's harder for us to boil them and turn them into gases. And branch alkanes are smaller, and so they would prefer to stay together than the long chain ones. Remember that when we talk about solubility of different molecules in water, that hydrocarbons do not like to go into water, but hydrocarbons do like to be in nonpolar solvents, like things like themselves, like gasoline or oil. Those things will dissolve together. So alkanes are nonpolar. They like to be with things like oil, and they do not like water. And the last thing you need to remember is the chemical reactivity. So alkanes have 2 important chemical reactions. They will burn. So if you have a fuel, anything with carbon and hydrogen, so wood is an example, gasoline is an example, you have to have oxygen, you have to have a spark to make it start, and then you'll always produce carbon dioxide, water, and you'll get energy out of it. So that's the purpose of combustion, getting energy to do useful work. The other thing is alkylation or halogenation, another word for it. Take a hydrocarbon, add a halogen to it with a catalyst, like light, and you can form a chlorinated or halogenated hydrocarbon. And all those hydrogens are bumped off, and you replace them with the halogens. That's another important one. So this page and the physical properties page, this slide's very important, and this slide is very important. So good luck with this chapter, and we'll move on to alkenes soon. Thank you. See you soon.